Let's think of a wire which extends from x1 to x2 on this coordinate system, and it has a constant current I flowing in the positive x direction. At this point P, what is the magnetic field created by this portion or this section of the wire that extends from x1 to x2? So this is our coordinate system, and the point P is chosen so that it has a vertical distance of r to the x-axis that the wire is onto. And we may also draw these dashed lines starting from the starting point of the wire to the point P in question. Well, we want that what is the point magnetic field at point P, both direction and the magnitude. And this dashed line is the straight line extending from the end point of the wire to the point P. We may also, locate these endpoints by just giving these angles. This is theta 1, and this let's call theta 2. Okay, these angles are measured from the vertical axis, the AY axis, from the dashed lines. And once you know what the theta 1 and theta 2 is, that means you know the starting point and end point of the wire. Point x2 is given by this formula, and this we have discussed in the earlier lecture. This is the integral from x1 to x2. It is, the integrand is ds cross r divided by r cubed. So these are the endpoints, starting point and end point of the wire. And we have discussed what the integrand is before, but let me also go over that. So what ds is, in fact, any infinitesimally small length element which is on the wire. But since the wire is located on the x-axis and is a straight wire, that means you divide your wire into very small, infinitesimally small length elements. And I will just pick up one of them at any point of the wire. Let's just for the sake of generality, pick up this piece, and I will call this piece as ds. So what ds vector is for this choice of coordinate system, since it's a length element and it's on the x-axis, it is dx, and since it's a vector, we have to put I, which is the unit vector in the x direction. Okay, so, and what is r? This is cross product, and the r extends from the source to the point in question, which is the displacement vector. Okay, so that means we have to let me grab my let me draw that displacement vector r by using my ruler. So that's it. This vector is starting from the ds, okay, location of ds, and going to the point P in question, and this is your displacement vector, which is this one. Okay, so, and also let's take this line, making angle with the vertical axis to be theta, right? For that means, since the starting point is x1, the starting angle for r1 is going to be theta 1, and since the end point is x2, that means at this point the r vector is going to have an angle theta 2 with the vertical axis. Okay, well, in fact the angle is this one, but I'm just taking the angle between this line that extends over the r vector, displacement vector, and the vertical axis. So anyway, next thing is that, you know, we have to calculate this ds cross r. I mean, we have to calculate this ds vector, which is again another displacement vector, which is very small, and in fact it's infinitesimally small, and it is having the magnitude of dx, with this vector r extending from the starting point, the tail of ds, toward the point P. Okay, this is your r and this is your ds. So make a cross product out of these two vectors. So if you think about it, and if you apply your right hand rule, that, you know, you always take the four fingers in the direction of the first vector. This is the first vector over here, and this is the second vector, and your palm is toward the second vector, and your thumb will show you the direction of the cross product. So wherever you take this ds vector, either over here or anywhere in between, you will notice that this cross product is always shows out, you know, out of the page. So that specifies the at least the direction of the magnetic field created by overall this wire, and it's always going to be out of the page. Okay, so whatever the magnitude is, it's going to be out. So we always denote the vectors which are out of the plane to be a dot with a circle. Alright, so we know what the direction is. The rest thing is just to calculate the magnitude. And the other thing is that since this angle is theta and this angle is 90 degrees, if you think about the magnitude of ds cross r, it is nothing but, you know, dx, because the magnitude of this, multiplied by r, the magnitude of the second vector, and multiplied by sine of the angle phi. And phi is the angle between the r vector and the ds vector. That means this angle. Okay, that is the angle. But if you look at carefully what this angle is in terms of theta, it is nothing but theta plus 90 degrees. So phi is nothing but theta plus pi over 2. Alright, so sine theta, why I'm doing this, because I want to express at the end of all this, I want to express this phi in terms of all thetas. Okay, because my endpoint is theta 1 and starting point is theta 1 and end point is theta 2. I want to just convert this phi to be theta. So there's nothing but you know, it turns out to be dx times r times cosine theta, because, you know, sine theta plus pi over 2 is nothing but, by using the trigonometric identity, you can just check this, is nothing but this is cosine theta. Alright, so far it's going good, because, you know, we only take care of the magnitude of the magnetic field now, and we just take care of this magnitude of this cross product, and it is there. So the only thing is that the rest is just calculate this integrand with these new variables. But if you look at carefully about these variables, when you go from point x1 to x2, all of these are changing. X is changing. Well, what is x over here? Since we are taking this dx, x is nothing but the position of the ds vector, the tail of the ds vector to the origin. Okay, this is x. Okay, if this is x, this is going to be dx. So and the other thing is that, you know, when this ds vector and r vector starting from point x1 to x2 they're all changing. Theta is changing, r is changing, and x is changing. My claim is that if you can express this integral in terms of one single variable, which is theta, the integral will turn out to be very simple to take. Okay, so that means if you change the variable for this integral to theta, that means you will have somehow d theta, and x1 is going to be converted to theta 1, and then x2 is going to be converted to theta 2, because in terms of angles, x1 corresponds to theta 1 and x2 corresponds to the theta 2. So if you look at this picture, the geometry of the problem carefully, you will figure out that x, there is a relation between this x, r, and theta. So this x is nothing but r times tangent theta, right? This is this right triangle, and this is theta, and this is 90 degrees. This is x, and this is r. So it's very easy to see that x is going to be r times tangent theta. And on the other hand, r is also can be expressed in terms of small r, which is the magnitude of the hypotenuse multiplied by cosine theta. Okay, we'll just use these identities in order to convert all these expressions into one simple expression, so that inside the integral we only have variable theta. Okay, so if x is r times tangent theta, then what is dx? So calculating dx is just easy. Capital R is constant, and if you take the differential of tangent theta, is going to be secant square theta d theta. Okay, so and the next thing is that, well, what is secant theta is nothing but cosine theta inverse, or 1 over cosine theta. Okay, and if you look at then this expression that ds cross r, and it turns out to be r times secant square theta, right, d theta multiplied by small r. Well, small r in fact is larger than capital R over here, because this is the right triangle, and the small r is just hypotenuse, and capital R is this vertical distance. And we have cosine theta, and let's also divide this by r cube, because we have inside the integral this division by r cube. That is going to be r square. Okay, so if you work all on this, that, and this second identity, if you look at it carefully, small r is equal to just the secant theta times r, right? So that means r square is nothing but capital R times secant square theta. So let me write it over here, that small r is equal to capital R times secant theta. So r square is going to be just capital R square secant square theta. So let's replace this by capital R square secant square theta, right? And this further simplifies that this 1 over r is going to be there, and this r is going to simplify, and we will only have 1 over capital R cosine theta d theta. So you see, this integrand over here turns out to be simplified, and it has only one variable. Well, capital R is just constant, and our integral will turn out to be just cosine theta d theta integral. So my claim was, just if you express everything over here in terms of angles, and the integral will be very simple to take. So I was right. Then what I do is just, I will rewrite this integral with the magnitude of magnetic field mu 0 I 4 pi. And now the integration limits are changed to theta 1 and theta 2. We have 1 over r cosine theta d theta. So this integral is very easy to take, and as a result, well, cosine theta is sine theta is the integrand, and derivative of sine is just cosine, mu 0 I divided by 4 pi r, and it is sine theta, and the limits are theta 2, theta 1. This is going to be mu 0 I divided by 4 pi r sine theta 2 minus sine theta 1. So this is the result. In turn, sine theta 1 is nothing but x1 divided by x1 squared plus r squared in square root, and sine theta 2 is just x2 divided by x2 squared plus r squared in square root. Okay, so that's it. You can either express the result in terms of angles or in terms of endpoint and starting point of a straight wire.